objective of the H2R project is to demonstrate that human-like locomotion and posture can emerge from a combination of neural, biomechanical, and cognitive mechanisms found in humans.
The H2R project is composed of 3 parts. The first part, we identify the biological mechanism of posture and walking. In the second part of the project, we formalize this mechanism into simulated and real-life robotics. At the same time, we design and build a new compliant human-like biped called Pinocchio. In the third part of the project, we developed a benchmarking framework for the assessment of bipedal locomotion functions.
In Freiburg, we developed a human-like controller that replicates the ability of humans to embed their movement execution control into the supporting posture control tasks such as body balancing, buttressing, and movement coordination. We call this controller DEC, that stands for Disturbance, Estimation, and Compensation.
Yeah, here at the University of Kaiserslautern at the Robotic Research Lab, we are focusing since years in the control of biped locomotion. With the University of Freiburg, we have integrated postural control, also findings from neuroscience in our control approach.
We deploy the behavior-based implementation of the DEC on anthropomorphic 21 degrees of freedom simulation of a biped. We apply the same disturbances as used in Freiburg's lab environment to validate the DEC concept.
To get P4LC a step closer to a physical system, people from the Robotics Research Lab visited Freiburg several times. The goal was to integrate the behavior-based implementation of the DEC principle on the post-rope too.
The DEC concept leads to a modular control design that can be applied to multiple degrees of freedom robot. Coordination between joints emerges from the interaction between control modules. This generalization applies to both planes and allows the robot to balance in the three-dimensional space.
At the University Medical Center in Göttingen, we focused on understanding the neuromechanical principles of human walking, and we did this through human experiments and modeling. In the project H2R, we developed specifically a musculoskeletal model that is able to generate human-like joint torques and stiffness.
We developed a controller that predicts the neuromuscular activation during walking at different conditions, such as different elevations or different speeds. We also developed a tool for its online integration in a robotic platform based on event detection.
We first modeled how muscle excitation primitives contribute to modulate movement mechanical variables, including joint torques and joint stiffness. We then demonstrated how this modeling approach can be used to control a simple biped using OpenSim and the SimBody physics engine.
Inside the project, we have done mainly research work with Göttingen in the range of integrating the impulsive control to our simulated biped.
We integrated our primitive-driven musculoskeletal model into the B4LC framework. The model generates physiological muscle excitations across a large range of locomotion conditions and produces human-like joint torques for the robots.
Pinocchio is a humanoid that embodies a compliant activation system called MACEPA, which emulates the biomechanical properties of human muscles.
The main advantage of the MACEPA is its mechanical transmission that can adjust its rigidity according to the biomechanical requirements of the biped.
So far, we successfully tested compliant actuators in all the activated degrees of freedom of the robot, which show a smooth and fast response.
Pinocchio has been designed to integrate all the control algorithms, sensors and actuators developed in the project. After testing the different mechatronic and software components, we have now achieved a full integration into one robotic platform.
The third important goal of the project was to identify a method to properly assess bipedal locomotion function. In collaboration with other European projects, we developed a benchmarking scheme and discussed it with several communities. Recently, we developed a web page in order to share different benchmarking protocols in an easy-to-use and interactive way.
In conclusion, the legacy of the H2R project is threefold. First, we developed a number of bio-inspired control schemes for human-like control of walking and posture. Second, we built a fully compliant biped that, together with its simulator, will be made available to the robotics community. And third, we created a new benchmarking scheme and a web-based application that is ready to be used.